So we covered the Carnot, and we're basically in a review of the vapor compression refrigeration system. We'll get to multi-stage, but not today. So one thing we need to introduce is property diagrams. So what we have is the standard setup for vapor compression refrigeration. So saturated vapor at state 1 is fed into the compressor. It's superheated vapor. It comes out of the condenser as saturated liquid. Then it goes to the expansion valve. It flashes through the expansion valve and then evaporates in the evaporator. Well, on a TS diagram, we've seen this, have we not? So you put at the low pressure at state 1, and it goes, this is a line of constant pressure, low pressure, and this is a line of constant high pressure on a TS diagram. So if you go from state 1 to 2 and you do it adiabatic and reversibly, you'll get to 2S. It's isentropic. If there are some irreversibilities, you kick it out and there's state 2 actual. And then you cool at constant pressure till it's saturated. So it goes from superheated to saturated vapor. Then it continues to cool over. So it's at state 3, which is saturated liquid. Then it goes, and there's no way to have a reversible expansion through that expansion valve. It's just a restriction. And so it's irreversible, dashed line, S increases, and there is state 4. There is a quality at state 4, maybe it's 30%. By mass, 30% of the fluid vaporized, leaving 70%, or whatever the number is, of that to vaporize and provide cooling. Now we have a new property diagram, a pressure enthalpy diagram, pressure and enthalpy. So you put the dome on it. The critical point on the TS is right at the top. The critical point is still at the highest pressure, but it's shifted over from, it's like skewed over. So it's a little funny that this curve bends right in here, but this is all a state of saturated liquids. This is all saturated liquids. I'm sorry. All of these states are saturated vapor. All of these states are saturated vapor. All of these states are saturated liquid. All of these states are saturated liquid. So we still have a dome on a pH diagram. But as you can see, the enthalpy, this is like H of G, starts to decrease as you get really close to the critical point, where at lower values of pressure, the enthalpy increases as you increase pressure. But then it curves and it decreases. So why do we like pH diagrams, especially in refrigeration systems? Because this system naturally splits to a high side, pressure high, and a low side, pressure low. And often you just need 2 pressure gauges and you can tell a lot about the health of a refrigeration system. So you have a pressure high and a pressure low. Okay, so the lines of constant pressure they're just horizontal lines. Let me get rid of this here. Get rid of that. Okay, now where is state 1? It's saturated vapor at low pressure. Go along a line of constant S, which they do on a lot of charts do have them, but it'll be shaped like that to state 2S. And then if it's some irreversibility, you'll come out with higher energy because there was more work put into the system than the minimum work required. So H2 will be greater than H2S.
That diagram line was a line of constant
Entropy, yes. Did I say enthalpy? No. It's a constant S, true? From 2 to 2S, from 1 to 2S is constant S. And then you go ahead and cool it so it's going from superheated vapor to saturated vapor, and then you continue to cool it until you get saturated liquid, and then at state 3, you're at saturated liquid, high pressure. You put it through the expansion valve. Now here it's irreversible again, so we want to draw it as a dashed line, but it's going to be straight down because it's isenthalpic, true? Isn't H4 equal to H3? H4 is equal to H3. I see a couple thumbs up. That's great. And then in the evaporator, you evaporate the mass that's still in the liquid form. Some mass flashes, true? So that's why you have a quality. Notice, what is the visual magnitude of the quality off of this pH diagram as I've sketched it? What would you say the quality is visually, just looking at it? How much? Yeah, it's state 4. What's the quality at state 4? Okay, we got 0.3. And so what you're doing is you're looking at the length of 2 lines and doing the ratio, true? How far is state 4 from saturated liquid towards saturated vapor? The length of this line divided by the length of that line is the quality. So if state 4 was way over here, what would the quality be? Very high, maybe 95, 97%. So sitting right here, you look at it and you say, it's about 25%. How's that? 25% look good? Looks good. So that tells you the quality there. Let's now talk about the refrigerant lines. There's 2 long lines for a residential air conditioning system, okay? And we'll talk about the automotive application in a minute. But the 2 lines are for refrigerant to flow back and forth from inside and outside of the house. So it's continual flow in one line and continual flow in the return line. Now, once it gets up to this A coil, here's a blow up of an A coil, it'll come in to the smaller diameter line. It'll return out of the larger diameter line. What is being supplied to this A coil? What is it in that line coming in? Liquid. Liquid, right? So what's coming out going back toward the compressor? Vapor. Vapor. That's right, vapor. So the liquid requires smaller cross-sectional area for the same mass flow rate than the vapor. The vapor has a larger specific volume or lower density, and it requires a larger cross-sectional area, hence you give it a larger diameter. Now, if you can trace this right here, it goes over and it goes into this right here. I'm going to change color right here. This is a restriction. That's our expansion valve. Now, it's got a control to it, and it's a TXV, thermostatic expansion valve. It's got a little bulb of a temperature sensor that goes over here and measures the temperature or senses the temperature on the suction line. And then it says, oh, I'm coming out too warm, give it more refrigerant. I'm coming out too cold, less refrigerant goes in, okay? So it is some control mechanism. It's not electronic, it's just mechanical. They're old. They've been around for a long time. They're switching a lot of this stuff to digital, electronically controlled metering to that A coil. But once it goes, now drops the pressure right across here, and now you have a distributor. So it's got 1, 2, 3, 4 lines, and they snake over, and they start feeding sections of the coil, and it goes back, do a loop, back, do a loop, back, do a loop. So you can see these 180-degree elbows that redirect the flow back and forth in a serpentine path through the coil. And it's all finned on this side to promote heat transfer. It's sealed right in here, so airflow can't go there. It's forced to come and do a Z shape across the coil and come up. It's sealed up here, so the airflow can't. The air has to go through the coil. Now, once they have 2 feeds on this side, They come up here, you can see 1, 2 coming out, true? 2 coming out. And on the other side, there's 2 coming out. And they collect in a larger suction line, manifold. There's a little Z to it. It goes back and then it comes out this way. There. So there you go. There's the flow of refrigerant through that evaporator. It's called A coil because of its shape, and they're very common. Okay, the tray you can see collects the water, and there's little hookups to get the drain. The length of this line between the expansion valve and the evaporator coil is very short. Likewise, back here is the compressor. The suction line goes to the compressor, then it discharges from the compressor and starts to go into these condenser coils. It then comes out of the condenser coil, goes through a filter dryer, and the liquid line back up to into the house. So the length of the line connecting the compressor and the outdoor or condensing coil is very short. There's 2 long lines, see that, and 2 very short lines. So here's an illustration: compressor, condenser, expansion valve, evaporator. These are the lines, like this line, or this line, connecting the components in that line. 4 lines, 2 of them are relatively long in a residential air conditioning application, and 2 are relatively short, true? So how about the one going from the evaporator to the compressor? Is that long or is that short? This one going from the evaporator to the compressor. Long or short? Long. How about from the compressor to the condenser? Short. How about from the condenser to the expansion valve? Long or short? From the condenser to the expansion valve? Long. And then from the expansion valve to the evaporator? Short. And so this, they have names for the long lines. One is called the suction line. One is called the liquid line. Okay? And so looking at this one, the one connecting the evaporator to the compressor, it's long. Is it called the suction line or the liquid line? It's the suction line. All right? And over here, this other long one connecting the condenser to the expansion valve, that's the long liquid line, isn't it? Liquid line. Now, the names make sense. I mean, liquid's flowing in the liquid line. Why don't they say the vapor line? Well, because the vapor is being sucked or drawn by the compressor out of that evaporator. If you turn the system off, let it all come to equilibrium, the pressure is pretty well the same everywhere. When you turn it on, it'll start pushing up the pressure on the outlet of the compressor and drawing down the pressure into the compressor, and hence it's the compressor sucking the refrigerant out of the evaporator. So that's why they call it the suction line. Now, I can see these 2 lines right here. Okay, where is the suction line in this automotive application? Where is it at? It's basically from the evaporator. I know there's a little metering device all the way to the compressor. Isn't that the suction line? And then where is my liquid line in the automotive application? It's right here coming out of the condenser. I know it goes through a filter dryer, but it goes all the way up. And this metering device is really close to the coil, so it's basically right there. That metering device is just like in the other one. Because as soon as you come across that metering device, it's cold. You want to get it into the evaporator. So that's the liquid line. Now notice that this line right here, you can often find that easily underneath your hood, because it's got to come out of that compressor and go and find it and connect it up to the coil the condenser in front of the radiator. And often it's long and it has to be able to handle the vibrations and other things. Okay. Now, one of these lines, the suction line or liquid line, is hot. And if you grab it, either under the hood of the car when the engine's been running and the air conditioner's been running for a while, you won't grab it for very long. It'll let go. And the other one will be relatively cool. You can touch it and it'll be cool. And actually, when it's running, if anybody's seen it, what will happen to that line? It'll be sweating. What do you mean sweating? It'll be so cool that it'll be below the dew point of the humid air around the engine, and it'll be drops all over it and it'll be dripping. Okay? That's how cool it is. So which line is hot? Is it the suction line? Is that the one that's hot? Or is it the liquid line hot? The liquid line, we have a vote that the liquid line is hot. People agree? And the suction line is cool. And in the automotive application, you could probably put your hand on this one. That would be a discharge line. Discharging from the compressor, going toward the condensing coil, condenser, and that'll be really hot. Right? You touch that, you're going to burn. Okay? Now, which one is insulated? Which of these lines are insulated? The suction line insulated or the liquid line insulated? The suction line is insulated. So why is the suction line insulated? Because as it goes through the, it's cool enough that it would absorb some heat from the surroundings, but it's not going to help performance. And actually, if you bring in the cool refrigerant into the compressor, it keeps the compressor from getting so hot. So it's better to feed it saturated vapor that's not superheated vapor, relatively cool saturated vapor. It's good for the compressor to feed it saturated vapor, not liquid. Don't feed the compressor liquid. It'll break. But you don't want it to be superheated vapor. It actually provides cooling to that compressor. Think about the temperature change coming in versus going out. That refrigerant really does boost the temperature. It goes way up. I'm sorry? Yep, all that work of compression just boosts that pressure and the temperature. It goes way up. And without any heat transfer, it's all just compression. And then, so here you can't really see this discharge line. It's so close from the compressor to that condenser coil. But you have two lines, the thinner liquid line and the larger diameter suction line. And one will have typically a big black foam insulation wrapped around it. One will be bare, right? The suction line will have that big foam insulation around it. And if you have cats and animals, they'll come around there and claw it and rip it off. True? Or it'll degrade if it's in the sun. And so you should try to keep that line insulated. And if you take that insulation, peel it back, and touch that line, it'll be cold and often wet to the touch because of the condensate. And then the bare line is the liquid line, and a lot of times you touch it and you'll burn your finger. It'll still be so warm. Okay? So it's uninsulated. Let's solve a problem. So we have refrigerant 134A is the working fluid in a vapor compression refrigeration cycle. The evaporator pressure is 1.8 bar. So this evaporator is at a pressure of 1.8 bar. And they tell us the corresponding saturation temperature of the refrigerant is negative 12.7 degrees C. Superheated vapor exits the evaporator. So it's not saturated anymore, it's superheated. And it exits at negative 10 degrees C. It's still really cold. But at that pressure of 1.8 bar, the saturation pressure is negative 12.7. It's coming out negative 10. So it's superheated by 2.7 degrees C. That's the degree or amount of superheat. 2.7 degrees C. True? You see that? The compressor isentropic efficiency is 88%. and the condenser pressure is 9 bar. So the high side pressure is 9 bar, the low side pressure is 1.8 bar. And the corresponding saturation temperature is 35.5 degrees C for that pressure of 9 bar. Now it exits subcooled liquid, not saturated, subcooled liquid at 31 degrees C. So if it exited as saturated liquid, it would come out 35.5 degrees C, but it comes out 31. So what is that? 4.5 degrees subcooling? 4.5 degrees C subcooling? True? Now the refrigerant flow rate's 5 kilograms per second. What is the rate of heat transfer to the refrigerant passing through the evaporator? That's Q dot E. And that's going to be the mass flow rate times enthalpy 1 minus enthalpy 4. True? We've solved a problem like this before, and that's the equation. What is the net power to the cycle? That's going to be to run the compressor. That's going to be the mass flow rate times H2 minus H1. True? And then the coefficient of performance, COP, is going to be the ratio of what I want, a lot of cooling in the evaporator, to what I have to pay for to run that compressor. So the answer for part A and B, the ratio, is the answer to part C. We have a nice illustration. You can get a property diagram, maybe a temperature entropy diagram, and go ahead and sketch the dome. Go ahead and sketch lines of low pressure, sketch lines of high pressure. Go ahead and put on state 1 is superheated vapor at that low pressure. So it's out there somewhere. And then it would go up to 2S, but it actually kicks over to 2 actual on a dashed line at that high pressure of 9 bar. And then state 3, if it came out saturated vapor, would be over here, but it's slightly subcooled, so there's 3, subcooled at that 9 bar. And then it has an expansion over to 4 through the expansion valve, irreversible expansion. So there we go. So make a property diagram as well as a table. So we want to put state, and then the pressure in kilopascal, temperature in degrees C, enthalpy in kilojoules per kilogram, entropy in kilojoules per kilogram Kelvin. And often we talk about quality, although some states it's not defined. So state 1. Well, we know the pressure at state 1, 180 kilopascal, right? 180 kilopascal. And the temperature, negative 10 degrees C. Well, knowing pressure and temperature, I look up the other properties. And so we find that it's around 245.14 kilojoules per kilogram and 0.9485 kilojoules per kilogram Kelvin. And the quality is not applicable. It's not defined in the superheated region. How about now state 2? Well, we do it in a 2-step process. First go to 2S and then to 2 actual, true? So we know that we go all the way to 900 kilopascal and it's 0.94852. So see that? And so what fixes the state is the pressure and the entropy for state 2S. We really calculate the enthalpy, 279.09. You can also calculate the temperature for fun, and it's 44.6 degrees C. It's non-applicable for quality, it's superheated. Now consider how much work the compressor has to do for isentropic compression. That's the change in the enthalpy. And we find that that's equal to 38 38.57 kilojoules per kilogram. Using the isentropic efficiency of 88%, the work the compressor actually has to perform is going to be greater. I just messed up and gave you this is the 38.57, and this one, looking at my notes, is 33.94. So more work is required than the isentropic work. So we get, for state 2 actual, the pressure is known, and the enthalpy is known, or calculated to be 283.72. So state 2 actual is fixed by calculation of pressure and enthalpy. We can now go and look up the temperature, and we find that it's now 49.0. It's higher temperature, isn't it? That makes sense. It's even higher temperature at state 2 actual. Look at 2S versus 2 actual. Look at the temperatures of those on a TS diagram. Okay, this again is not applicable for quality. Now we go to state 3. What information was given? It's 900 kilopascal, and it's subcooled to 31 degrees C. So we look up the value, and the enthalpy is 95.00. That's a dramatic drop in enthalpy, isn't it? All that because of cooling in the condenser. And if you wanted to, you could look up the entropy, but it's not needed. And the quality, unfortunately, is not needed either. So I should have color-coded this blue, because you look that up as a function of knowing the pressure and the temperature at state 3. Make sense? And then the last state, 4, we drop the pressure to 180. Isn't that the pressure in the evaporator? 180 kilopascal. And it is isenthalpic, so it's 95.00. And when you do that, you will find that it is two-phase. It's at negative 12.7 degrees C. I should color code that a little different. Negative 12.7 degrees C. And the quality is 0.2886. So almost 30% by mass is now in the vapor state. That's not going to provide the cooling. The 70% that's by mass that's still in the liquid state provides the cooling. That's what evaporates in the evaporator. Okay, so that's state 4 was fixed by knowing the pressure and the enthalpy. Well, you take the difference in the H1 and H4 multiplied by m dot, and let me just kind of tuck the solutions in somewhere without having to mess up my page. Q dot evaporator comes in at 12.5 kilowatts. And the W dot for the compressor, the power needing to drive the compressor, is only 3.21 kilowatts. And the coefficient of performance for the refrigeration system is 3.89. Any comments or questions about that? Doable? Good. Here is a summary of the whole thing. And so if you're watching this or want to watch it later and redo the results, you can do that, okay? And so everything is outlined here. You should be able to sketch it on a pH as well as a TS diagram. I think you can do that. What I wanted to do, though, is I wanted to show you how I did this in Excel. I think it's pretty doable. It'll just take a minute. So here is the Excel sheet, that I copied. So this is my style to help organize the work. What helps me fix the state, followed by the state, right? So this I could put bold and center. the pressure in kilopascal, temperatures, enthalpies, entropy, and quality if needed. State 1 does not have the quality of 1. Okay, so it comes in at that pressure and that temperature, and I use this call to this routine right here, right? Evaluate the enthalpy, knowing pressure and temperature of refrigerant 134A, given C3 is pressure in kilopascal and D3 is temperature in degrees C. If I have any questions, I hit this and it tells me more about enthalpy, kilojoules per kilogram. Refrigerant 134A is a function of pressure in kilopascal and temperature in degrees C, SI units. And if I want to do English, I just have to put ENG as a third argument, which I don't do. And there's the result. So that function is very useful, true, to help you navigate evaluating these. And then the same thing for the entropy. Entropy is a function of pressure and temperature. The next one, 2S, I just take and copy this one. See how it's copied down? So that gives me the same S. Don't have to do it by hand, but just copy it. And then pressure is known. 900 was given. This is evaluate temperature as a function of pressure and entropy for refrigerant 34A using that pressure and that entropy. And likewise the enthalpy, true? And then state 2, what I had to do is I do some work on the side. So the work isotropic compression for the compressor is the change in H1 to H2S. Oops. And then the efficiency, then you divide the actual or the isentropic work by the efficiency to get the actual work. So it's up, it's increased to 38 kilojoules. Use that over here to get H2 actual is H1 plus this work. True? All right. And then if you wanted to look at that temperature, evaluate temperature as a function of pressure and enthalpy. And then go to state 3. It was the pressure and the temperature were given. And you just look up the enthalpy as a function of pressure temperature. And if you wanted to, you don't need this entropy. You can get rid of it. You don't need that S, but if you wanted to have it, you could put it in there. And then state 4, the pressure and the enthalpy. It's just copied down from E6 and evaluate. You see the quality there is evaluated function of pressure and enthalpy. Calculate Q dot evap is the mass flow rate times the specific heat transfer in the evaporator, which is H1 minus H4. The specific work of the compressor is the same as we calculated over there, but you multiply that by the mass flow rate, you get the work net, the coefficient of performance, true? And something I didn't mention, but you measure the rate of cooling in RTs, tons of refrigeration. How many people have ever heard tons of refrigeration? Couple? So if you say your house is 2,000 square foot, you want to provide air conditioning for it. In the city of San Antonio, typically for every 500 square foot, you need 1 ton. So if you have a 1,500 square foot home, 3 ton air conditioner work. 2,000 square foot home, 4 ton. 25, it keeps going up, right? Now, if you have a very new home that's hot, it's tight, not a lot of leakage, and you have a very good insulation in the walls and the ceilings, roof, and all that, then that ratio drops. You don't need such a big air conditioner to be comfortable. But that's a good rule of thumb, okay? For every 500 square foot, 1 refrigerant ton. Well, 1 refrigerant ton is 211 kilojoules of cooling per minute. So this is basically calculating what is the refrigeration capacity of this system. It's 3.56 tons, refrigerant tons. So that's what this is on the side. Did that help? How many? This is pretty straightforward, can do. If you did this by hand, you'll find you'll have to do some interpolations and maybe even some double interpolations in the tables. So that's why the software is so much easier. But I can't trust students, unfortunately, with computers during exams. Somebody will just click over and then they'll be reading the solution manual or some PDF files, and I won't be able to police it. So that's why we don't have computers available in exams, because it's, unfortunately, that's why. It's not that I don't think I could make a good exam. It would be good to have exams like that, but you have to do it by hand in exams. True? All right, let's jump back and finish up here. Let's talk about selecting refrigerants. Well, this all makes sense. You select the refrigerant based on how well it performs. Does it give you a good COP for those temperatures that you want with reasonable pressures? You don't want astronomically high pressures in the evaporator or the condenser, because if somebody punctures it, you don't want it to act like a bomb, right? And things do have leaks in them. And the higher pressure it is, the more difficult it is. Safety. Some refrigerants are flammable. So if you have a leak, it could, with any spark around it, could, boop. Some refrigerants are butane and propane, ammonia. And then also the environmental impact has come on strong since the 1970s. Does it go out and do bad things to the environment because these systems will leak the refrigerants? They just will leak. Or maybe when it's decommissioned, they just cut it open and let it all escape. So that's just a reality. Synthetic refrigerants, man-made refrigerants, were developed in the 1930s because of toxicity and flammability of most of refrigerants before that time. So if it leaked out, settled on the floor, worker bent down to pick up a tool, got a big whiff, maybe they fell on the floor and they died, or something like that, right? It's toxic, not healthy to be breathing, and it could be an asphyxiant. Or maybe there was a spark, machinery running, boom, now you have a blow up. Okay, so in the 30s, they got a very great advantage of these synthetic. What were some of the most popular? R12. It was all over the place, still is. It's a chlorofluorocarbon, CFC. It's now been outlawed because of environmental concerns. R22, hydrochlorofluorocarbons. So used to be if you had an air conditioning system in an automobile, it was all R12. That's probably now before you were born. But now they're all 134A. Why did they switch? Not because of toxicity, not because of flammability, but not because of safety, not because of performance, actually. It's environmental impact. And almost all your homes are R12, but now they are switching those over. If you get a brand new system in a home, it's probably 410A. It's probably this one right down here. So all of these were being used, but in the 70s they found out about ozone, high level, way up high altitude. They were being gobbled up by these leaky refrigerants that go up there and interact with the sun. So they started banning the production of certain chlorine, that's the bad actor, in these refrigerants. And then they had to develop new chlorine-free refrigerants. And so 134A seems to be the replacement for 12, and 410A seems to be the replacement for 22. And 22 you couldn't manufacture since I think 2010. 2010 they can't manufacture any equipment that uses it. So it's been, and then more and more gradually phased out. Soon you won't be able to buy it or manufacture it to maintain existing equipment. So just take a look at what they look like. You can tell this one, R22, has a carbon, a hydrogen, a chlorine, and 2 fluorines. And it looks like methane. So the C, the carbon, is surrounded by 4 things. 1 is a hydrogen, 1 big chlorine sitting out here, and then 2 fluorines. This is another illustration of 134A. So it has a carbon and a carbon, like 2 methanes combined and linked. And it has 2 hydrogens off of one of the carbons, that'd be the 2 hydrogens, and then a fluorine off, that's a green, and then off the other carbon, 3 fluorines, 3 greens. I'm not a chemist, but there you go. So there are different makeups of these synthetic refrigerants. Here is more on that phase out from the EPA. Went to the EPA website and took a look, and as of January 1st, 2010, because of the Montreal Protocol, the U.S., blah, 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 as a result, HVAC, heating, ventilation, air conditioning systems manufactured may not produce any new air conditioners or any new heat pumps that use R22. So it's now quickly going down the tubes. And you can see increased agreements that will be continuing to kick in. And eventually they won't be able to even use any of the recovered or recycled or reclaimed. Will be allowed beyond 2020. But chemical manufacturers no longer able to produce. So that's what it is. You'll be able to use it if it's been reclaimed, but you won't be able to produce any. Right now, the pound cost of refrigerant 22, it just continues to skyrocket. So what it used to be, it's probably at least a factor of 4 or 5 since 2010. Just so it's going to go out by economics. One other thing, other than the high level ozone depletion, and they characterized a lot of refrigerants. Here's a lot of refrigerants, and they would look at the ozone depletion potential. And long bar to the left is bad, short stubby or if no bar is great. True for ozone depletion. But there's another thing. It's called global warming potential. How well does it act like a CO2 blanket in the atmosphere, not damaging the ozone, but helping trap and have, they just call it climate change now, but global warming potential. And then, so for the same refrigerant, you can measure how bad it is for global warming potential. The larger the bar is to the right, in the blue color, the worse it is. And so what you want to pick are environmentally friendly refrigerants. And so, again, R410A seems to be one that's popular, and R134A is very popular. Okay, with that, we're done for today. Thank you for your attention.